Welcome back to the Genesis Science Report. For all of the advances of modern science, one of the most basic questions still refuses to go away. How did life actually begin? And the deeper researchers look, the more that question seems to center not just on matter, but on information. Inside every living cell is a kind of a digital code. It's precise, functional, essential to life itself. And in what many are calling the age of design, this has become one of the biggest reasons that the origins conversation is shifting. The issue is no longer just whether life is complex. The issue is whether the information at the heart of life can really be explained by chance and chemistry alone. Joining me in studio is Dr. Stephen Meyer. He's a philosopher of science, author, and leading voice in the intelligent design movement, whose work has focused heavily on the origins of biological information. His books include Signature in the Cell and Return of the God Hypothesis. And more recently, those broader design questions have also been explored through his current film project, The Story of Everything. Dr. Meyer, great to have you.
Nice to be with you, David. Thank you.
Absolutely. Yeah. You know, we were talking just a moment ago in the intro and in the green room about complexity, but there's a difference between something being complex and something being complex but orderly or engineered. Talk about that for just a second.
Well, yeah, in the information sciences, there's a kind of threefold division between things that are merely random. You could think of the characters that the monkeys type at the typewriters, the famous monkey at the typewriter example. Sometimes people think of that as complex, but then another distinction is between the complexity or randomness and orderliness, which is the idea of just a simple repetition. So that would be more like a mantra. Or a crystal where you have a repeating structure, NaCl, sodium chloride, sodium chloride, sodium chloride, and then something that is both specified, or both complex but also specified.
Okay.
Something that where the sequence is, it's not simply repetitive, and so it's complex like the random sequence, but it's where there's the complexity is very precise and needs to be arranged in a very specific way in order to achieve an independent function. And that's what we have in language. You know, we don't have just the, or we have an aperiodic, unpredictable arrangement of characters that is specified by some independent symbol convention that allows the arrangement of those characters to convey a message or to perform a communication function. And interestingly, of those three types of sequences, DNA is not merely complex, it's not merely random, it's not ordered in the sense of a crystal, but rather it's specifically arranged in the sense of like a language or like a section of computer code. And the name for that in the information sciences is specified complexity or specified information or specified or functional information. There's different terms for it, but so DNA is like a software program. Our software mogul in the Pacific Northwest has said, Bill Gates, but much more complex than any we've ever created.
Right, and much more vast than most people can imagine. The amount of information, specified information and complexity.
Yeah, it's stunning. In the human genome, it's about 3 billion characters. In even the simplest cell, you're looking at probably 3 million characters and hundreds of proteins.
In the age of
DNA codes for building proteins, that's the reference there.
I got you. Yeah. In the age of design that we are living in, when you think of biological information, we think DNA, we think things like base pairs, but it's so much more complex than that because then you have proteins and other structures, right?
Well, we not only have a long linear molecule called DNA that encodes information in a digital form, but the information on the DNA strand is read by a system of protein machines that express that information and allow the information to build yet other protein machines And we need those protein machines to stay alive. The proteins do all the important jobs in the cell. They catalyze reactions, they form the structural parts of miniature machines, like the ATP synthase, a little turbine that creates the energy-rich ATP molecules that drive all metabolic processes, and the proteins that are built by the information on the DNA strand, in turn, some of them, in turn, are necessary for reading the information on the DNA. So you need the DNA to build the proteins, but you need the proteins to express the information on the DNA. So you have this very difficult chicken and egg problem that has stymied origin of life researchers from the outset.
Okay, so if we're talking about materialistic, naturalistic processes, lots of time plus evolution, well then you might get one given vast, vast probabilities, which most, I think our friend John Lennox would probably say mathematically improbable, which means impossible.
Well, there's a concept in probabilistic reasoning called the probabilistic resources. Okay, so if you have a thief outside the building here wanting to steal a bike, and encounters a 4-character digital bike lock. If the thief has only 5 minutes to try different combinations, it's much more likely than not that he will fail to crack the lock by chance, okay? If he's got more time, and I've made this calculation, if he has 15 hours to spare and he's willing to change the combination once every 10 seconds, after 15 hours, he will have generated 5,001 combinations, say. At that point, it becomes more likely than not that he will succeed by chance, and therefore the hypothesis that it happened by chance becomes plausible.
With 4 characters.
With the 4 characters. But the problem is with the proteins, a modest length protein of say 150 amino acids, where you have 20 different amino acid possibilities at each site, generates such a vast number of possibilities to be sampled that, and I've done the math on this, that if every event since the beginning of the universe had been devoted to searching for one of those combinations, there would not be enough opportunities to get to even more. I think it was like 3% of the total. So it's much more likely than not that the chance hypothesis, that chance arrangements will fail to find a functional sequence, and therefore the chance hypothesis is more likely to be false than true. And then when you consider that we're not dealing with just one protein in a cell, but hundreds, and many are much longer than 150 amino acids, it doesn't matter whether the universe is 13.8 billion years or 20 billion years, there's simply not enough opportunities for things to happen by chance alone. And this, by the way, is universally accepted among serious origin of life biologists. Nobody is pursuing a chance hypothesis to explain the origin of life, because there's so much information that trying to find it by chance alone is not plausible.
Here at the Wonder Center and Science Museum, just down the hall from where we're sitting, we have this colorful creations. It's a kid's game where they can basically put colored ping pong balls in different configurations on a lighted board. Right? And I started to count the number of different colors that we had and do that math and realize, well, the chances of any one child doing the exact same design as anyone other in the history, if everyone in the United States was to come here, is so mathematically the probability is so low.
In a way, we shouldn't waste more time discussing this, because nobody's taking this seriously in origin of life research. The chance hypothesis is just dead. And so, yeah, people have moved on. They've tried to explain the origin of information in some other way by reference to natural laws. But the problem there is that natural laws produce or describe strictly repetitive patterns. They describe order, but they don't describe specified information or specified complexity. So as you look at the different possibilities for explaining the origin of information, there's really only one that's plausible, and that is intelligence. If you think about any informational sequence you know, a section of software, the text that's written on your notes there, information embedded in a radio signal, information in a hieroglyphic inscription, I could go on, but you trace information, functional information, specified complexity as we've described it, back to its source, and you always find a mind, an intelligent agent, not an undirected, unguided process. So the discovery of information at the foundation of life is a powerful indicator of the activity of a designing mind in the origin and history of life.
Yeah, that's absolutely fascinating. You mentioned the chicken and egg problem, because even if you could get one portion of it, you need both simultaneously, just like an engineer who's building a car needs to have both wheels and a steering wheel before the car is actually usable.
When you have those types of functionally interdependent systems, and we trace those back to their sources, they always come to the need for intelligent engineering.
Wow.
You need something from outside the system to put the two things into the proper relationship with each other. If one depends upon the other for its existence, it's not going to get the whole system started until the other part is put into proper relationship with it, and that invariably requires engineering.
And let's just back up for just a second, because with classical Darwinian evolution, you can have a survival of the fittest component to this, but if you've got half of an organism that is fit for survival with this one half made, right? That's not going to stick around waiting for the other half to be formed.
This is the problem of irreducible complexity that Michael Behe has highlighted with the miniature machines that we're discovering in cells that require often several dozen parts working in close coordination. If you have an incompletely built machine lacking one or few of those core parts, there's nothing there for natural selection to select. So it seems to be an inadequate mechanism for building these types of functionally integrated, irreducibly complex systems. And in the new film that you mentioned, The Story of Everything, which is out in theaters April 30th for people who are interested, we have animations of these miniature machines and also this whole information processing system that's at work inside the cell, where you have the digital code in the DNA molecule directing the construction of protein parts at a kind of molecular factory called a ribosome. And you can actually see that process at work, and we can share some of that animation with you and your viewers even in this program.
I can't wait, and I can't wait to see the documentary, The Story of Everything. Dr. Stephen Meyer, thank you so much for joining us in studio.
Thank you for having me, David.
Absolutely. And that is it for today. I want to thank you for joining us on the Genesis Science Report. Until next week, I want to remind each and every one of you, you are designed. You are living in an age of design. Start looking at where science is heading. It's all pointing us right back to an intelligence. I'm David Rives. Until next time, keep looking up. Truly, the heavens declare the glory of God.